and this presentation is about the evolution of the facial animation technology. And all this didn't happen overnight. It took actually almost 3 years. And as you can see here, we generated a lot of new buzzwords along the way. And even in the, there's a lot of stuff. And even in the office, we are sometimes not really sure what all this means. So I hope we can put a lot of things into context in the next 50 minutes. And the best way to do that is to go for the material in chronological order. And I hope you still remember this one. It's a Senate speech with Admiral Bishop. And when we worked on this scene in 2015, we did everything with traditional methods. And that means everything was animated in Maya. And then we baked the result into an animation file. And that's OK if you have only a simple cutscene. The problem with this approach is when you have multiple cutscenes in the same game and you want to use them. That's a bit tricky. So we used this system before when we worked on other games. And I think it's a pretty good workflow for pre-rendered cutscenes. And it's still OK if you want to use it in-game for a couple of unique characters. But it's absolutely not practical if you have a game with lots of interactive situations and where every character has a different face. The amount of data you need to duplicate is absolutely insane. So it was clear for Squadron and for Star Citizen we had to find a different solution. And then Trilateral proposed a new solution, and that one was radically different. It's based on an animation rig that is running in the engine. And that basically means we take all the heavy work that usually happens in offline tools, and then we put it on a CPU and execute it at runtime. And when I heard that, I had absolutely no idea what the impact on performance is. That's why we should take a look what an animation rig is actually doing. So when an animator animates a face in Maya, then he doesn't animate every vertex or pixel individually. Instead, he's using a tool like this one. It's called a face board. And it has a set of sliders, and each slider is connected to a region in the face. So when we move the slider for the eyes, it's not only moving the eyeballs, it's actually moving a lot of little details around the eyes, like the eyelids, the eyelashes, the eyebrows, and it's also driving the wrinkle maps and the blend shapes around the eyes. So with a single slider, we can control all these microscopic details in a certain area of the face. And a face board is basically a simple UI for an animator. And it's also the input system for the animation rig, which is always running in the background to make sure these little details in the face get a correct animation. And as long as all this happens in Maya, it's called offline rigging, because everything happens in an offline tool. And now, with runtime rigging, we decided to take this system and move it directly into the engine. And it turned out that actually has some advantages. With offline rigging, each face, and I mean only the face alone, was using about 600 joints. And that's really a crazy number. And one of the problems with offline tools is you generate a lot of data. And then you need to store that data somewhere. And in our case, it was just convenient to bake the metadata for the blend shapes and the wrinkle maps directly into the joints. And if you need 402 joints only for the blend shapes, then you can imagine why the joint count is totally out of control. With runtime rigs, you don't need any joints for metadata. You generate everything on the fly, and then you can use it immediately to drive the skinning joints, the blend shapes, and the wrinkle maps. So after we switched to runtime rigs, it turned out we can delete 70% of all the joints in the face. All we need are these 179 joints for skinning. And runtime rigs are also highly efficient animation compression system, so mainly because we don't need to store that much data. All we need are a set of 183 input parameters per keyframe. And that makes all animation files automatically 5 times shorter. So the data size went down by 80%. And this compression is lossless, because now we can generate everything on the CPU at full floating point precision. And now the elephant in the room, performance. With runtime rigs, we can update 10 heads in 1 millisecond, and that's actually almost a double speed compared to offline rigging. And yes, we still need to do a lot more computations at runtime, but now this all happens mainly in the cache of the CPU, and that's the reason for the speed up. And it took, of course, some time to organize the rig data into a cache-friendly and compact format. And these numbers here are only for the animation update on the CPU. They do not include rendering or shading, but Andreas will talk more about this later. But I think 10 heads in 1 millisecond on an i7 is a really good number. But animations are not the only reason why we switch to runtime rigs. Another pretty big advantage is what we call runtime retargeting of animations. And in my opinion, that's the absolute killer feature. And here are some examples. Targeting means you can play that animation on every face model in the game, even on faces that look totally different. And it can be a simple facial expression that shows only the mood of the character. So if he's happy, angry, or sad. Or we can take the full performance of one actor and then play it on any face model in the game. And it also works the other way. We can take the performance of different actors and play it on the same face model. So here you have Jax McCleary and Bellosa and some experiments I did. And it's the same face model on all these screens, but the performance is coming from different actors. And this transfer of performance to different faces, that's a pretty big deal for us. Without runtime rigging, it's pretty much impossible. The only option would be offline retargeting in Maya, and that means brute force data duplication in the engine. And if you have 120 unique faces in the game, then you can imagine how much data you need to duplicate. Yeah, and the next feature was also inspired by runtime rigs. And you know that, face over IP. And in this case, we record the voice and the facial animation of a player with his webcam. And then we convert that performance into facial controllers, which we send over the network. And then we reconstruct that animation on different clients. And in this case, we take advantage of two main features of runtime rigs. The first is the compression feature, because we want to send only a few input controllers over the internet. And the second is the retargeting feature, because we need to reconstruct the facial animation of a real player on his avatar, which might look totally different. And the next feature is called performance transformation or PCAP transformation. And with this feature, we basically try to modify an entire pre-recorded mocap scene at runtime. And this here is an original mocap scene without any procedural modifications. And the pure mocap scene is pretty much like a movie, and the performance of all the actors is fixed. But this scene here doesn't work as expected. These two guys are supposed to look at the player and talk to the player. And in a first-person game, the player is always the camera, so they are supposed to look directly into the camera. But here it looks more like they are talking to an invisible person in the room. And a scene like this can only work if you watch it from exactly the same camera position it was captured for. But if that cutscene is interactive, and in Squadron most cutscenes are interactive, then the player can be anywhere in the room, and the camera is always at the wrong position. So here we have the same scene again, but this time with PCAP transformation. And we still have only one animation per character. And one of the challenges we had to get right was the body language of the NPCs. So when Sito opens his arms and says, "Welcome to Stanton," then you expect him to turn around in his chair and really face the player. And that can be a challenge because the player can be anywhere in the room. And another challenge is the eyes. NPCs need to make eye contact. And that's where the runtime rigs come into play. Yeah, you can do all these experiments. So that's where the runtime rigs come into play. And with runtime rigs, you need to modify only a couple of parameters to make them look in a new direction. So, and then everything around the eyes, like the eyelids and the eyebrows and the wrinkles, everything gets a new transformation. And that blends very nicely with the face and body animations. And this is a feature we developed on our side, and then we combined it with the runtime rigs. So all the features I just mentioned are a direct result of runtime rigging, but we have another one in development, and I hope this one sounds familiar because Freelateral presented a prototype last year at the GDC. And today we take a look at an updated version in our engine. And gene splicing means you have a database, which we call a DNA file. And in this DNA file, we have a couple of scanned heads. And each scanned head has a fully working rig logic to drive the facial animation on a character. And this database or DNA file is what you can call a gene pool. And this confused guy here is the base model. We call him the average Joe. So if you take all the heads in a database and average them, then you get this face. And that's how we generated the average Joe. And now we can take different features out of this database and build our own face. We start with the eyes, and we give him the eyes of his mother, and the nose of his father, and I hope that is big enough. Okay. And then we can change the eyes, and they can be different on the left and the right side. And then we can change everything around the mouth. And that's a very important thing here. The left and the right side of the face can be totally different. Yeah. So the days of symmetric faces are officially over. Yeah, that's what I want to say here. So, and then of course you can change the shape of the head, and with a little bit of tweaking and artistic skills, you can create a new face in a couple of seconds. It doesn't take that long. And that's pretty much the concept of gene splicing. You have this database with a couple of scanned heads. And then you say, I want the nose of that guy and the ears of the other guy. And Freelateral calls it shopping for face parts, because that's what it actually is. And the face is subdivided into these 12 regions, and for each region we can blend in multiple parts of different heads. So I think it's a simple system, but at the same time a really powerful system to generate new faces in no time. And maybe you noticed I'm throwing all these buzzwords around, like gene splicing, DNA pool, and what else? DNA system. And when I heard these words the very first time, I had absolutely no idea what all this mumbo-jumbo means, at least not in the context of character customization. So gene splicing, that's the buzzword for these 5 features. And these 5 features represent the skinning and the transformation rig of a character. And that's it. Now, if we change something on a head, then we need to regenerate all of them on the fly. And because this is still a bit mysterious, I will just show with a video what's really going on under the hood. So first, we have the mixing of the base mesh. And that's the most obvious feature, because you can see the shape of the head is changing. But there is another little detail, and that's not so obvious. We can also change the geometry inside the head, like the shape of the eyes, the tongue, or the teeth. And especially the teeth are important. Each head has the mouth at a slightly different position, and you need to make sure that teeth are placed correctly inside the mouth. If you don't do that, then it can happen that they just jump out sometimes, like in those alien movies. So, and then these green dots represent the bind pose of the character. These are the joints of the bind pose. And each character needs a bind pose. It defines how skeleton and mesh are connected. And the bind pose in general is static. You create it in Maya to bind the mesh, and then it stays like that. But here the mesh is morphing, which means we need to change it or update it as well. So these green dots need to be on the surface of the skin all the time, or the skinning will break. And the next feature is really hard to see if you don't know what to look for. Each character or each head has slightly different skin weights, and skin weights have a very big impact on the skinning. And the biggest impact is always around the eyes. And for gene splicing, we need to mix the skin weights as well. If we don't do that and they are not correct, then it can happen that the eyes do not close. Or you get the opposite, they overclose, and then the eyelids intersect. And people pay a lot of attention to eyes, and if something is not right, they see it immediately. And the next feature is called corrective blend shapes, and that's again a feature that's very hard to see or to debug. The only way to make it visible is to turn off all the joint animations and play only the blend shapes. Now, if you look at the character on the right, you can see he has this wobbling on his skin. That's from the blend shapes. It's very subtle, and it needs to be subtle, because we use it only for micro adjustments. With joints, you can move only a group of vertices around, but for all these subtle details where you need high precision animations, it's a lot easier to work with blend shapes. So, and then finally, we have the rig logic. And this feature is impossible to visualize. It's pure code with all the rules and heuristics. And the rig logic is like the puppet master behind the curtain. It controls just everything in a phase. And for gene splicing, we need to mix the logical data of all these different rigs together, or the facial animations will not work. So here you can see I'm morphing between all these different heads while an animation is playing. And it doesn't matter how much the face is changing. The rig logic will always make sure you get the correct expression on all these morphing heads. And that's the main purpose of the rig logic. It's responsible for the retargeting of the animations. And I think it's doing a pretty good job. It doesn't matter how strong the face is morphing or the rigs are changing. And that are the 5 features of gene splicing. If you have a normal head, then all this is static. But here we need to do a dynamic update of all these 5 features, which means we need to regenerate an entire facial rig from scratch, every frame. Of course, something like this needs to happen only in the customizer and only for one head. You don't need to do that in the game. So once you're done with customization, we bake everything into a static rig, and then it works like all the other heads we already have in the PTU. So with this system, we can generate every facial feature we want. And that means we have a procedural system to create an unlimited amount of new faces. But if you look now at all these variations, you can see they have one thing in common. There is no facial hair or any other type of attachments. It's just the skin. We can, of course, give them now baseball caps or beards or different hats or sunglasses, but then you get this. They just don't match. Yeah, they either clip through the skin or are detached from the skin. And all things like beards, hair, baseball caps, they are just skin attachments. In any game, you create them for one head with a fixed shape, and then you can use them only on heads with the same identical shape. But the whole point of gene splicing is to change the shape of the head on the fly. And that's a really hard case to crack, and I think it's the main reason why most games try to avoid unique faces, especially if they have lots of variations. It's easy to scan different faces, but how do you deal with the attachments? So there is one way around it, skull unification. So in this case, you unify the skull, the jaw, and the position of the ears. And that helps a bit, so it's still far from perfect. You can see, look at the beard, it's still clipping, but it helps a little bit with rigid attachment like sunglasses and this officer cap, because now the skull is static, but that means you can't change it anymore. And the only thing left for customization is now the mouth, the nose, and everything around the eyes. And that's better than nothing, but only if the face is directly in front of the camera. If it's 2 or 3 meters away, then this feature is a lot harder to see. And after 4 meters, it's almost invisible. So, I mean, just look at the guy in the distance. Maybe you can see that 3 pixels on his nose are still morphing. But that's not enough to say that this is a new face or a different head. So skull unification is a compromise, but a bad one. It's like deactivating the feature without fixing it. So that was an example why skull unification is a bad idea. And here's another example why I think it's an absolutely horrible idea to do it. We just ignore textures and facial hair for a moment, and focus only on the silhouette of the original scanned heads. The silhouette alone has all the key elements we need to identify a face. And it actually seems that the silhouette has a much bigger impact on our perception than all the features on the front side of the face. I know this sounds a bit counterintuitive, but actually it's not. Silhouettes have a very simple and clear image. They are used in any field where you need to identify objects very fast. That's why traffic signs are using silhouettes, because you can identify them in a split second from far away. And that's the other cool thing with silhouettes. The size and the distance doesn't matter that much. And if you look at all these heads, it's clear they all look different from every camera angle. And it's not the nose or the mouth or the eyes that makes them different. It's the shape of the head, and especially the size of the head relative to the body. That has a much bigger impact on our perception than all the features on the front side of the face. And with the skull unification, we just killed this feature. And then at this point, we had to make a decision. If we cannot find a simple solution to combine attachments with the original scanned heads and keep the silhouettes as they are, then there's no practical reason to continue with gene splicing. If we don't get, how to say, more bang for the buck, then this is just a waste of CPU cycles. It's like rebuilding a clone army with a more complex technology. And that was the reason why things didn't move forward with gene splicing. That's why it's not in any PTU build. We just couldn't find a solution for the attachment problem. So the gene splicing system was in a state of coma for a very long time, I think almost 1 year. And then beginning of this year, Andreas, he's sitting over there, started some experiments with wrap deformers in Maya. And he built a little prototype or demo to show how offline tools deal with this problem. And I mean the problem with the attachments. And he created something like a proof of concept, and that was a new inspiration for us to do some research in a new direction. And then a couple of weeks later, we started our first experiments with wrap deformers in the engine. And now you can see the beard and the hair is now perfectly aligned with the motions of the head. So, and we can morph between different heads, and we can animate them without getting any clipping. So game engines in general have only one deformer, and that's skinning with a skeleton. But the wrap deformer doesn't need a skeleton. Instead, you have one geometry, which is driving the deformation of another geometry. And in this case, we use the animation and the morphing of the head to deform the beard and all the other attachments. But that means now we have these interdependencies between attachments, so we need to execute them in a certain order. And that's a little challenge for a GPU implementation. It's not so easy to implement it or run it in parallel in a GPU implementation. So this all seems to work really nice, but there's one important thing to mention. What you see here are only elastic attachments that are glued to the skin so that they move with the skin. This is a special case. And for this special case, our simple wrap deformer gives us pretty much flawless results. Now the question is, what happens if we use the same wrap deformer for rigid attachments? Like, yeah, exactly, glasses and helmets. And you see it, it's a total deformation disaster. And here we have, and here actually we have an additional challenge with the DNA system that trilateral, guys, I need to stop the video. So here we have an additional challenge with the DNA system that trilateral provided. It is possible to create asymmetric faces. That means the left and the right side can be totally different. And we will, of course, make full use of that feature. So faces in real life are never symmetric. If you find one, it's most likely computer-generated. And in this video here, and in all the examples you've seen before, I'm morphing the left and the right side completely independently. But the big problem is now all the rigid attachments are now also asymmetric. And you can see the problem on these metallic helmets, so these metallic parts. They are warping in all random direction, and it looks more like, how to say, rubber than metal. So in other words, it doesn't work at all, and that means always back to the drawing board. And a couple of weeks later, we started the next generation of wrap deformers, and if you look now at these sunglasses and this officer hat, you can see there is this subtle scaling. It's just enough to align the attachments with the shape of the head. But there's one detail that makes this a bit tricky. Some attachments have parts that are elastics and parts that are rigid. And we want the rigid parts to stay rigid, of course, and not bend like rubber. And we want the elastic parts, like this helmet harness around the neck, to deform with the geometry of the neck. And that means we need multiple deformation methods for the same attachment and blend between them. And the only way to get all of that is to create the equivalent of a rigging system for wrap deformers. So here we are still doing experiments with different techniques. We are still trying to figure out what gives the best result. But what we are doing is we are measuring the proportions of the head after the morphing. Then we put those values into a bigger matrix, which we use to adjust the helmet. So we just apply some stretching and scaling to the parts of the helmets, if you pay attention here. And I think this gives really good results, and especially it preserves the shape of the helmet and all these fine lines in the helmet design. And you can see it here on the Star Marine helmet and the Slaver helmet. So all these new deformation methods, they give better results in many cases, but they are not automatic methods. They need a lot of fine-tuning, and that means more work for tech art. But what we have so far, so we are still testing this with all the assets in the build, but what we have seems to work, and that's something we can call hope. So, and here we have Admiral Bishop again after some cosmetic shader improvements. And this model is still work in progress, but I think it's a really good reference model. So what we have now is a face customization system based on gene splicing. And when we worked on this system, we had, of course, concerns that all the customized characters might look like second-class or low-budget characters, especially when you put them next to a T0 model and use the same camera and lighting. So what we have here is just a simple test to see how the gene spliced heads can keep up with an original head in terms of animation and visuals. And Bishop is the only one created by an artist, and the rest is what we call programmer art. There is no model on disk that looks like this. We created all of them with gene splicing, and we just took the most extreme features in one phase and combined it with features of another phase. And if you pay attention, you can see all of them are still morphing. And we also gave them some new attachments, some random attachments we found in the build. That's why they look a bit funny. But as you can see, all the skin attachments work without clipping, no matter if rigid or elastic. So now, if we take all these heads and put them next to each other and compare them with a T0 with an artist-created model, then I think it's not really obvious that all these 8 heads around Bishop are created by a user with a customizer. So I know it's a bit hard to compare the animation of 8 heads while they are playing at the same time, but this will be on YouTube in a couple of hours or a couple of days, I don't know. But then you can pause the video and compare every single frame if you want, every single pose, and you will see every micro-expression, every emotion is absolutely identical on all these heads. And that's very obvious when you focus on the mouth. The shape of the mouth and the lips are different on every head. But the retargeting works so well that we don't get any weird deformations or clipping. And it's the same for the eyes. They all look different. But they animate in the same way and always close correctly. And they show the same emotions and micro-expressions in every single frame. So Bishop is, of course, a T0 model. And that's why it has a higher resolution mesh and sharper normal maps. But all the technical features to animate these faces, they are identical for all of them. So each customized head has a new base mesh with unique skin weights and corrective blend shapes. And it also has a unique bind pose and rig logic for the facial animation. And that's what all these faces have in common. And in all this example here, I'm using always the same animation, only one animation. And I think the runtime rigs are doing a pretty good job with the retargeting. And especially this case here, especially in combination with gene splicing, that's the absolute hardcore test for animation retargeting, because we can generate millions of faces. And honestly, I have no idea what else we need to do to create a test case that's crazier than this one. And maybe you're wondering about these strange numbers on the screen. That's what we call the DNA matrix, and there are always 48 numbers in that DNA matrix. That's the input parameters for the gene splicing system. So every variation, every permutation of a head, it's encoded in these 48 numbers. And that's all we need to generate a facial rig from scratch. And you can see it here. I'm doing this non-stop morphing between different heads. And every time the head is changing, the numbers change as well. But it's actually the other way around. That matrix defines how the face looks. So when you customize your face in the game, then it's that matrix you need to send to the server. And yeah, that's it. That's all you need to do. Then everyone in the verse can see the new face on your avatar. Yeah, and this is also the end of my part about gene splicing. Thanks for coming. So next we have Andreas on stage. So my part was more about runtime rigging, and he will give you a lot more details about gene splicing, and he will also go into the future plans. So give a warm welcome to Andreas.
Thank you, Ivo. Oh, wait, it's still Ivo's presentation running. Sorry, wait a second. Gotta kill his one, sorry. Okay, open up mine. DNA. Sorry. Okay, let's get started. Oh, shit, damn it, sorry. Okay, so while Ivo has already given you the arc of this story of how this feature came together, I'm going to give you some more technical insight, even more under the hood stuff, and I'll also try to explain to you why this feature is so important in the context of our game. So it's really so important, has such a big impact, because in Star Citizen we don't have a limited play space. We have procedural generated planets, we have procedural generated cities, and at some point we just have to fill these places with life. And we have to fill the universe with a backstory, and that gets best told through characters. And you relate to all these characters through animation. You interact with them through their face. So that's why we don't want to have we don't have any background characters in our game, as Ivo has told you. We have these different tiers of facial rigs, but in theory, whether it's player-generated animation through face over IP, or whether it's animation that from mission givers, for instance, or gameplay story cinematics, as we call them, they all need to be at a similar level. And when these characters are standing next to each other, it shouldn't be obvious which is which. In order to do that, there could be several approaches. First, we could ask Trilateral to just generate 10,000 rigs for us, or maybe 100,000. That should be sufficient, so you don't meet any duplicate characters in the verse. But I think it wouldn't be money particularly well spent, and that's your guys' money, so we needed a cost-efficient solution, and that's a procedural solution for generating these faces. The paramount thing for us was that the player was able to customize their face at a very high level of detail. with infinite variety and customizability. But it's also very important for ourselves as developers. Our lore guys come up with all these interesting characters that have their backstories. The designers want to put them into the game, and they all need to have unique faces. So you probably know that we have this ratio of 9 to 1 with like NPC characters versus player characters. So for us developers, it's super important to have this system even at our own disposal. Yeah, and one requirement that the system needed to fulfill is that the customized faces should not look generic as they do in some customizers of other games that use a more parametric approach, making the jaw wider, the nose longer, pointier. You often end up with a similar looking face, a face that looks similar to the one you started off from. They kind of seem related. But in our case, because we blend realistic scanned heads from actual real human beings and blend them together, we'll never end up with a face that looks unrealistic. Okay. So most of you will probably be aware, but let me quickly give you an overview of our current state of facial customization. We have a very first version of customization in the game already. You can choose between select 9 faces, a fixed set of faces. You have no possibility to blend between them whatsoever. You can do texture swaps, of course, which gives some additional level of variety. But ultimately, like every 9th guy you'll meet in the verse at the moment will look the same. And because of the fact that we have unified scalps and necks, because of the limitations of our previous attachment technology, all these heads also look very similar, and we lose a lot of the characteristics that the actual real people had that originally were scanned in. So it was a valid first step for Star Citizen, and it gave you something that you could play with, something new. And yeah, it's iterative development, it's normal, but it's definitely not sufficient for Star Citizen, and that's why we went a step further and tried our best to solve all these problems and get gene splicing working. While Gene Splicer is a very powerful technological foundation, it's important to say that this system completely relies on the heads that are in the gene pool, as we call it. So currently we have 122 heads that we scanned. Most of them are actually for Squadron, so you haven't seen them yet. The problem with these heads is they are not really totally representative of an entire population. So they were cast, most of them were cast specifically for Squadron, and because Squadron is a space opera, sci-fi, game, film hybrid, there's a certain bias in terms of what faces you see there and what characters you see there. So most of them are male, obviously. In terms of age, they're probably 25 to maybe mid-40s. Most of them are fit military types because they serve on some spaceship carriers. So it's not like a proper representation of a population. And in order to do that, the heads that we ultimately want to put into this pool need to basically match both ends of like a spectrum of all these different categories that you see here, which is, obviously gender, it's a race or ethnic origin, age, of course, very important. We also have quite a few older backers who probably want to have avatars that look like themselves at some point, or maybe they actually want to look young, I don't know. Then there's physical constitution, which is also like visible eventually on the face. And then there is attractiveness, whatever you call pretty or ugly. We want to have all these things covered, at least in terms of NPCs. You want to have a nasty-looking mission giver if he's, because you can tell a lot of the story just by how a person looks. So we think that ultimately this will probably require between 50 and 60 select heads altogether for both genders. We're going to treat females and males separately. And while this perfect gene pool requires maximum variety in terms of the number of heads that go in there, for the attachment system and the shape preservation system to work, it's actually the exact opposite. So in order to make it easier for this solver or for these algorithms to work, we actually need to create the perfectly symmetrical average of all these heads that go into the system. And then when the face gets customized and the attachments get deformed, they have statistically they're likely to have the least distance to travel, and the shapes will be preserved more easily. And in order to help the solver, we run a certain markup process in Maya, which is what you can see here, where some metadata gets attached to the polygon structures, which get then exported into the engine. Then Evo's code reads this data and applies it at runtime, and then you see all these nice-looking faces that you've just seen. Okay. So while Gene Splicer is a very powerful technological foundation done by 3Lateral, it's important to point out that the tech demo that was showcased at GDC in 2017, I think in spring, it was just a tech demo, and back then it hadn't been implemented in a shipping product yet, and I think it hasn't up to this point. So whilst we wanted to use this system, we had to kind of be the pioneers that had to squash a lot of bugs, work very hard together with 3Lateral, and actually solving all these problems, one of them being the attachment problem that Ivo mentioned. And the first part of this video shows you this little mock-up that I did in Maya, digital content creation application, that finally convinced the guys to pursue this approach in the engine. Maybe the fact that we could even apply beards to females convinced them in the end, but all right. So another thing that we needed to solve, you may not be aware of, in games, typically, every asset that you see doesn't exist in just one version. So for instance, the head or the head of this guy, every object in the game exists at different resolutions, and depending on the distance of an object to the camera or to you, and on maybe the system specs, whether you have a fast machine or a slow machine, the most appropriate one of these meshes gets picked. And with the gene splicing system and our attachment system having to adapt these meshes at runtime, we needed to make sure that's also supported. It also supports this level of detail LOD system. And as you can see here, when your character traverses the verse or walks through a level, there are constantly new player or non-player characters that come into your view. And when they do, the first moment they get rendered, their runtime rig will already must have been created. And that process, I think at the beginning it took 60 milliseconds or so, which is pretty long when you think that there could be a dozen or a few dozen characters popping up immediately when you enter an area, like area 18, where there are many characters at some point. So that was way too long. So Ivo did a lot of optimization there together with 3Lateral to bring this number down. But it's not only about creating these runtime rigs fast enough at runtime when you traverse through the level. It's also, even if you're static and standing still and all the other characters were standing still, you still need to render them efficiently. And because now with the system, we're able to have maximum variety and no duplicate characters, we'll probably want to put more in the game, so we have to render more. And our rendering tech needs to keep up with that, and our deformation tech as well, which is closely related. Sorry. So the next slide, or the next clip, I need to give you a little warning, because when I started, you're going to see a super low frame rate, probably the lowest you've seen in the context of Star Citizen. And you've seen a lot, I'm aware of that. All right. So let me just start this. And it's really slow, but there's a very good reason for that. So this is a grid that I procedurally generated of 100 characters. And as I said, normally this LOD system makes sure that the ones farther away get rendered at a lower resolution in order to not have as much load on the CPU or GPU. Now in this case, I forced what we call the lot 0, which is the highest resolution mesh, intentionally in order to stress test the system and really hammer the CPU. And that's because especially this this LOD0 of the faces was traditionally, for technical reasons, in our game or in our game engine, was always computed on the CPU. And then data had to be sent to the GPU, and that's always a bad thing. That's always a bottleneck. And we wanted to get rid of that eventually anyway, even independent of gene splicing and the DNA system. But because we had to overhaul our deformation system in order to make this attachment adaptation work, we had to do that anyway. So we thought, okay, that's a good opportunity to kind of kill two birds with one stone. So one of our core engine programmers in Frankfurt, Andrei Pivnenko, he went ahead and implemented a GPU solution for deformation also on our lot zeros. So we're going to use that across the board at some point. So this solution is based on compute shaders that are currently running on DirectX 11 and will ultimately run on Vulkan. And when they do, they're going to be even more efficient and give even better speedups. So what you've seen here, like even in terms of frame rate, I just got to swap back. You saw speedups like 12x, which is already quite impressive for like a first iteration of this system. And when you actually look at the subtimings, because here are like a lot of other factors that factor into the actual frame rate, but when you just compare CPU and GPU subtimings, we already now see like larger than 20x improvements of speed. And while you'll not have like frame rate improvements overall in the game just because of that, in a real world scenario, these will have like a way less impact. Like normally in terms of optimization, it's like every little bit helps, you know? There's the millisecond here and 2 milliseconds there, and our core engine programmers, they often fight really hard for this stuff, and then tech artists come in and just double the polygon count, and then that optimization is gone again. So yeah, another thing we did, in particular Evo did, was to reduce the memory footprint of these rigs. And because they have all these blend shapes, I think every rig has around 400 blend shapes that are essentially copies of the mesh at a slightly different shape. These things were huge, like historically at some point, and we now were able to reduce this memory footprint to just a very small amount, and that doesn't necessarily help with like average frame rate, but it really helps with loading times and with like your minimum frame rate. So it's quite important for a good play experience in the game. So as I told you, even we as a developers are going to be using this customization system in order to populate the world with NPC characters. And for that, we need an internal tool. And that's currently the first, like an early version of that, first iteration. The development of this tool will inform the development of the user-facing one, the one that you'll end up using at some point. And like currently, yeah, you can select the heads from the pool. You currently have 4 slots, and you can choose the ones you like the most and you want to blend between. And once you made your choice, yeah, you can assign these weight values to each head, and thereby influence the shape. Depending on how much effort you want to put into this, you also have these like these sub weight blend areas that you can fine tune. So when I skip forward a little bit, I think there are some that for which this feature is not very important. They just want to skip this, don't put much effort into this, but especially like the role players amongst you, they want to make sure they look exactly the way they want, I guess. So one of the kind of neat features is this randomize functionality, which you can use, which assigns random numbers, and that gives you like a starting point, and if you like that, you can go from there and improve your face further. Right, we're also able to assign certain like test animations and test loadouts to these in this customizer. That's quite useful for debugging and seeing how the face reacts, how the attachments react to the various shapes. Okay. All right, so what's now you're probably wondering when you guys can get your hands on this system and start using it yourself. So currently, we started like very early days of developing the user-facing interface. As I said, that gets informed by the internal one, and so yeah, one step after the next. One of our gameplay feature teams is also soon going to start implementing the persistence feature, so these 48 tiny values that make up the entire shape of a face, they need to be stored persistently in our database. Once you've done with your customization, you don't want to lose that. And then they will need to be transferred over the network. So the guys, like your fellow players that see you, meet you somewhere in the verse, they see the face that you customized. Yeah, we also need to port all the existing attachments that we already have in the game to this new system. It's just a matter of just working through them. There are not that many yet. And yeah, ultimately, the goal is to replace all our non-tier 0 characters. So all the characters and all the rigs that are not the super Hollywood actor ones, we're going to replace with a gene splicing system, which will give us huge memory savings and generally simplify our pipeline overall as far as characters are concerned. So currently, as far as I know, according to our roadmap, this feature is slated for release in 3.5. When it does come, it should come with female heads, because by the time we should have females in the game in general. And yeah. It's going to be exciting. Yeah, then the first iteration probably won't have this full gene pool of 50, 60 heads to choose from, but there will be probably 12 or 16. So you'll have like a lot of variety to choose from. And so now that this is out of the way, like focus of R&D can now shift to other parts of the human body that you can potentially customize. And that's something I'm super excited about. You can see some first examples here, just as a teaser. It's going to be even more exciting when you're talking about females, but that's something for another day. All right. So that brings me to the end of my sub-part of our joint presentation. Special thanks goes out to all these individuals listed for either contributing to the implementation of this feature and also to helping out with the content for the presentations. Special thanks, of course, to 3Lateral for the amazing gene splicing system and their great collaboration while implementing this into our game engine. And biggest thanks of all to you guys out there for supporting us, for hanging in there. Last year's CitizenCon I watched myself. I was a backer since 2012. I still saw, from your perspective, now I'm here. It's amazing to have your support. And when we go through when we solve these hard problems, it's always important for us to know that you got our backs and we got your support. So thank you so much for that. And that's all.